Hey everybody, how's it going? So Detroit Wrecker made a video in response to the videos I made about him. And he says nobody would go into a store to get the 7806 and ask for a 7806 voltage regulator IC, right? He says they would go in there asking for a 7806 transistor. And well, no, they definitely wouldn't. So if somebody needs a 7806 voltage regulator, what they will more than likely do is they're going to go in and they're going to ask for a 7806. Or they'll go in and ask for a 6-volt voltage regulator, or a 6-volt regulator as they're more commonly referred to. Nobody is ever going to go in and ask for a 6-volt regulating transistor. Nobody's going to ask for 7806 transistor because there's no such thing. Now, like I said, they'll probably go in there and ask for a 6-volt regulator, or they'll ask for a 7806. Now, saying that somebody's going to ask for something like that, that's like saying somebody's going to go in to buy one of these 555 timers and say, I need a 555 timer IC because it's an integrated circuit. Or this LM356, they're going to say, I need an LM350, 358, sorry, not wearing my glasses, 358 dual op amp IC. No, they don't say IC. Just because something's an integrated circuit, nobody ever asks for any integrated circuit as an integrated circuit. It's like saying, well, let me get some of these 386s, right? I say I want a 386. Person behind the register, he knows what he's doing. He's going to know I'm looking for an LM386 operational amplifier. Typically a power amplifier, but this one right here only delivers about a quarter watt, so it wouldn't necessarily be a power amplifier, but that's the way it's classified as a power amplifier, but that doesn't really fucking matter, now does it? Now, you said that for me, it would be something, but see, typically, don't ask for 6-volt regulators. I usually get 5-volt regulators, and this is what I wanted to point out, This right here is a 5-volt regulator. 5-volt regulator. And if you look at the back of the package, right, I don't know if you can read that. It looks a little fuzzy from my perspective, but if I can get the phone to get off of me and read that. It says NTE 1951 integrated circuit 3-terminal positive voltage regulator. It's right there, integrated circuit, not transistor. Now, if you were to go in, and this is another thing that you should probably be aware of, right? If you go in and you say, oh, where are your transistors, right? And they ask, what are you looking for? You say, well, I'm looking for the 7806 transistor. They're going to look at you funny because they've never heard of 7806 transistor. But they're going to point you over to the transistors. Now, when you're over at the transistors, you'll find all kinds of transistors. NPNs, PNPs, P-channel NFETs, N-channel JFETs, JFETs, N-channel JFETs, P-channel JFETs, enhancement mode MOSFETs, depletion mode MOSFETs. You'll find all sorts of transistors, but you won't find any regulators. And if you're looking for the 7806 regulator and you ask for the transistor, you could be sent to the wrong place and looking in the wrong line and get really upset, because you're looking for this component and you're looking in the wrong place for it. So understand that you're looking for a voltage regulator, not a transistor. And if somebody's looking for a specific voltage regulator, they will either ask for the 7806 voltage regulator like you were looking for, or something comparable. See, go back to this guy right here. See, this guy right here, this NTE 1951, is a 5-volt regulator. How did I get this? I was looking for a 7805. They didn't have 7805, but they had that, which is on paper, identical. And in performance, it's identical too. I got two of them. The other one is in something, gone away. But I got another one just in case. But as I was saying about Detroit Wrecker and his inability to go beyond the scope of the kit that he's working with, I typically like to use these regulators. This is an adjustable regulator. It will go from 1.5 volts all the way up to 37 volts. It can be run off of any supply ranging from 3 volts for the 1.5 volts all the way up to 40 volts. And with 40 volt supply, it can go up to 37 volts. It's a handy bit of technology to have, and it's really easy to set up. All you're going to do is look at the data sheets. You can see everything you need to be able to use this for any voltage that you desire. Now, this is, let me see if I can read this. 2578T, and then there's an ADG or ADJ for adjustable. But what I really wanted to point out was this guy right here, right? This big ass metal thing on the back. See, the 7806 is capable of handling up to 1.5 amps with proper heat sinking. So that's an important thing, because the way Wrecker has it set up, it'll only handle up to an amp, and you're probably not going to be running at that full amount. But what's really important that I want to touch out about that doesn't really include either of these components is what I have on my breadboard right here. Because if I'm in need of a regulated voltage, this is probably what I would do instead. Something like this. What I have here is 3 resistors really. The fourth resistor here is actually a current limiter for the LED there. We have 3 resistors, a transistor, and a good old Zener diode. All of these things together give me a well-regulated voltage. At this setting, it should give me 6.25 volts with an input of anywhere between 7 and 15 volts. After 15 volts, it starts to get a little bit less regulated, but the transistor here isn't able to handle that much power anyway, because it's just a real simple transistor made for low power operations. If I wanted to do high power, I would want to use something more like this guy. This is I believe a tip 32. Tip 31, yeah. Tip 31. This guy right here can handle high currents, and if I need to go higher, I can attach a heat sink onto there and go up to, really any level I desire, but I have to stay within the power capabilities of the components that I'm using. So to keep everything kosher, I guess you'd say, I built this little regulator using the transistor and the LED and a resistor there to give it a current, and I turn the switch on. The LED comes on, letting me know that I have the full 6 volts. It's at proper brightness for the 20 milliamps that it's pulling, and I've got the voltage on my supply here at 15 volts. I'm getting about 60 milliamps going through the entire circuit, well within this little transistor's capabilities. It's well regulated on the positive side, on the input side. I can go anywhere from like I said, about 7 volts all the way up to 15, and keep the voltage within a reasonable range of the 6 volts that I was aiming for when I built this guy. Could I make it for different voltages? Sure, just change the Zener diode to whatever I need it to be, and bada bing, bada boom, it's regulated, right? But I very rarely need these things, right? Not a lot of circuits call for it. And really all this is the internal circuit within one of these things. Just a different value of Zener, right? This is a 5 volt, that's 6 volts. But the functionality is the same. I look at Detroit Wrecker and he says that, oh, people just call it that because it's a common term. No, that's not common. Nobody calls a regulator a transistor. Nobody. And if you're curious as to what this looks like, this is what it looks like. Yeah. I put a little switch here so I can turn it off. See? Off. On. Off. I should probably show more about this because, you know, voltage regulation is kind of a neat thing. I've got it set up with 6 volts and 20 milliamps on the output. You know, that's a pretty standard current for an LED. The LED is a 2 volt LED, so, you know, approximately 2 volts. So knowing this 2 volts, 20 milliamps, you should be able to tell me what this value of resistor is there using Ohm's law, you know. You got 6 volts with a 2 volt voltage drop, 20 milliamps. That's everything you need, right? So that's fun, right? But that's it, right? That's all. Anytime you see a regulator, you understand it's not a transistor. And just because something is an integrated circuit doesn't mean that it's being asked for as an integrated circuit. Like the 555 timer, definitely an integrated circuit, right? Nobody's ever saying, wait a minute, man, what's a 555 timer? It's a fucking integrated circuit. But nobody goes up and says, I need the 555 timer integrated circuit. It's assumed an integrated circuit by the people who work there because they know what the fuck they're doing. At least I would hope, right? I've been to several supply stores and not once have I walked in there and said, hey, I need this thing. And they're like, I don't know what that is. And I have to explain to them that it's an integrated circuit, right? Never once. Now, the other thing that you like to talk about, impedance, right? I saw your little thing where you're sharing that little data sheet from the guy or whatever the fuck you call that, where he's talking about how an amp works, and he's talking about impedance, and he's talking about how thin and thick the impedance is. You understand that's not telling you any fucking thing about impedance, right? Assuming that impedance is AC and that resistance is DC, well, I mean, it kind of helps, I suppose, if you're trying to learn this stuff, but you should understand that's not a full picture, right? And it doesn't really tell you anything about resistance or impedance. Understand, though, that resistance is impedance, but impedance is more than just resistance. Impedance is a vector sum of both the real and the apparent power losses in the system. So it's a total combined effort of all the components together at whatever point you're measuring. So you look at your amplifier, right, where your speaker plugs in. It's the output impedance. So where does that output impedance come from? Well, if you're an educated man, you might take a look at what's going on there, and you'll see it's the secondary of the output transformer that you have there. It's the resistance of that secondary output transformer. That's where that impedance is coming from. That's almost all of it, right? So you look at other amplifiers and you find the same thing, you know? Output transformer, the resistance there, that's where that impedance is coming from. It's all coming from that transformer. And you're sitting there going, well, it depends. If it's AC, it's impedance. If it's DC, it's resistance. You're fucking bending over backwards to try to justify the stupidity that you're exuding, not really understanding. The more you talk about it, the more everybody can see that you have no fucking clue what you're talking about. So, does it matter if we're talking about AC or DC? Not really. I mean, look at your capacitor, right? Capacitor. The higher the frequency, the lower the impedance, right? So what do you get when that frequency is 0? That's right, you get an infinite impedance, right? Just makes sense. It's an infinite impedance. So, if you have an infinite impedance at 0 hertz, 0 hertz is DC, right? It doesn't change. 0 hertz. A DC signal will not pass through a capacitor. So if you were to put a 5 volt DC signal on a capacitor, you get 5 volts you got a 5 volt drop across that capacitor. It means all the power appears to be being consumed at the capacitor. So if that's the case, why doesn't the capacitor get hot? See, because it's not really consuming power. It just appears to consume power. It's apparent power consumption. That's impedance. Even though you're dealing with a DC signal, you're getting an infinite impedance across that capacitor. It doesn't have infinite resistance. And you can tell because resistance remains the same for AC and DC, and you start pumping some frequency into there, you start seeing less and less voltage drop, and you start seeing more and more of the signal coming through. So the impedance becomes less and less as you increase that frequency more and more. So, this whole notion that impedance is AC and resistance is DC kind of goes out the window as soon as you bring up the fucking capacitor. Right? The inductor, you get kind of the same thing, right? Put a 5 volt DC signal across here and you see almost 0 voltage drop across this thing. 5 volts streaming straight through there, offering 0 resistance. But you start putting some fucking frequency across this thing, and all of a sudden you start seeing more and more voltage drop going across this thing. And no matter how much voltage drop you get, this thing doesn't really seem to get very hot, right? So it appears to be consuming power, but it's not really. Again, that's impedance, not resistance. I mean, there is some resistance in this thing, but it's very, very small. I mean, here, I can fucking measure it for you right now if you'd like. How many ohms do we get? .4 ohms. 400 milliohms. Virtually nothing. But you put a high enough frequency across this thing, and no voltage will get across it. The higher the frequency, the more impedance it has. That's impedance. At 0 hertz, virtually zero impedance. Now you take this resistor right here. Let me just measure it because I don't have my glasses on to read the color codes. I should just put the clips on there. This dog in my hands, it's a little bit harder to move these things around, but all right, 150 ohms. right? So it's 150 ohms. That's resistance. Doesn't matter if I put an AC or a DC, it's going to get some level of voltage drop across there, and given time, it'll get hot, right? That's because it's dissipating real power across it. That's your lesson in impedance versus resistance. Now, these things don't have thickness or thinness. A high impedance isn't going to cause something to get thin or thick. Low impedance isn't going to cause something to get thin or thick. In fact, those terms, high impedance and low impedance, they're kind of arbitrary, right? Look at your guitars, right? Your guitars have between 10 and 100K of impedance. 10K, is that a high impedance or is that a low impedance? And it really depends on what you're plugged into, right? If you're plugged into a high impedance amplifier, 10K seem kind of low, right? 10K compared to a meg is pretty low. But if you're plugged into something else, something like maybe 5K, right? 10K is pretty high compared to 5K. So it's an arbitrary thing. Now, there are three phase or three state chips, right? They're digital, right? But they have three modes, right? High, low, and high impedance. So high is high, the voltage is high. Low is low, voltage is 0. High impedance is that there is a voltage there, but the impedance is so high that there's no current, right? So with no current, the voltage is hard to read. It's basically an open, but with voltage behind it. And you can set things to read the 3 different modes and operate just like any digital. But for most digital objects, the high and low is all that is used. The high impedance is a third option that's been developed more recently, as an option to program and operate these different types of components. You'll see it in microcontrollers mostly, right? But it's going to show you how this thing is regulating the voltages so well, because you can see it's a 6 volt supply, or 15 volts going into this thing. I have this resistor, which I can't remember the value straight offhand, but it's going into the collector. I believe it's maybe 200 ohms. It's hard to see from here. I don't have my glasses on. 200 ohms. Now next on my base here, I have a Zener diode, 6.8 volt Zener diode, going from the base to ground. I also have a resistor here. Again, don't know the value. Let's take a look here. 200. 200 what? 200K, right? So 200 ohms, 200K. Then on the output I have, on the emitter I should say, I have a 2 mega ohm resistor going to ground. And what that is just to set the so I can open it, right? I can open it and measure the voltage and see the 6 volts. Here I have, I believe, a 200 ohm resistor going to this yellow LED, with the yellow LED is about 2 volts forward voltage. And I believe that's 200. I'm not going to bother with it. It's around 200. And that is it, right? That is all we need to establish this 6 volt regulator. And it is current. It is stable, right? It's about 6.2 volts, starting at about 7 volts. Now, if I go below 7 volts, it starts losing regulation, right? The reason being is because, well, we started out with 7 volts, right? 7 volts, there's a about 0.7 volt drop between the base and the emitter. So that 0.7 volts there, it's already going to be taking it below 6, right? 7 minus 0.7, 6.3. So we're already really close there. And we start trying to do anything more like hook up this LED. It might still work, right? But it's going to start being a little bit dimmer. Just doesn't have enough current to keep it going. And of course, the lower we go, below 6, for this to be a 6 volt regulator, it needs to be able to get at least 6. Well, turn off that meter. So I've been thinking, I want to see how this regulates at higher and higher currents, right? How high of a current can I put it? My problem is that this transistor can only do like, I think, 1/8 of a watt, something like that. Let's see, 60 milliamps. Across this whole thing. Yeah, it's actually getting pretty close to its limit now. It's like this 15 volts that I put it at, that's what I did my calculations for the max voltage. And much higher than that, and we lose regulation much higher than this. So we start getting like closer to 7 volts, It's like, right now I think it comes out at like 6.5, right? 6.2 is the regulated value that I started with. And of course, it does have a little bit of dropout allowed for it. So getting up to 6.5 is within a quarter volt. So it's still considered to be well regulated, but much more than this, and it starts going up, and we start getting closer to 7 and 8, and then things start getting hot and burning up. There's no fucking heat sink on this thing, but everything's staying really cool, so that's a plus. And I'm using this capacitor to hold my voltage leads in place. So I have the ground connected to the switch, so I can turn it off at ground. That's pretty cool, I suppose, right? But this is a regulator. It's a real simple circuit. Not a lot to it. You really just have to calculate what you're going to use for your resistances. And of course, I could always use a bigger resistor like this if I wanted to move up to more and more power, but I don't want to burn up the transistor if I don't have to, right? All right, well, that's really all I had to say for today, Peace out.